Okay, in this video I'm going to go through how to determine the pH of an acid-base reaction. Here we have a polyprotic acid, specifically H2SO4 or sulfuric acid, and we're going to titrate it with 0.5 molar sodium hydroxide. I made the concentrations the same so it's a little easier to see where we're at. And what we're going to do is we're going to go through all 5 points of interest. So 50 milliliters of sodium hydroxide. Clearly the sulfuric acid will still be in excess. 100 milliliters of sodium hydroxide, the first equivalence point. 150 milliliters, so in between the first and second equivalence point. 200 milliliters when both of those protons from sulfuric acid are used up. And then finally 250 milliliters where the sodium hydroxide is in excess. So starting with A, 50 milliliters. The original chemical reaction here is going to be H2SO4 is reacting with NaOH to form HSO4 minus. So the first thing that's going to happen here is one of those protons is going to get given up. And water, so that'll be the combination of that hydrogen and those hydroxides, and sodium ion. So in the first situation, keeping in mind that my concentration is equal to my moles over volume, so my moles is equal to concentration times volume. Here, for my concentration of 0.5 molar and my volume of 100 milliliters or 0.1 liters, I have 0.05 moles. For sodium hydroxide, doing the same calculation, 0.5 molar. And now I only have 50 milliliters or 0.05 liters. Now I have 0.025 moles. So I've created a situation for A where the sulfuric acid is in excess. This is my initial number of moles. This is going to be my limiting reagent. And so what's going to happen here is that this is going to react away quantitatively until I'm left with none of this in 0.25 moles. There's 0.025 moles of H2SO4. To determine pH, I need concentrations. So if I have 0.025 moles of that remaining, and I have a total volume of 100 plus 50, then I have a final volume of 0.15 liters, or a concentration of 0.167 molarity. Now with that in hand, keeping in mind that H2SO4 is a strong acid, when it is left to continue to react with water, it'll form H3O plus HSO4 minus. This will continue to react to produce more hydronium, but the amount of hydronium that it produces is small because it's an equilibrium situation, so we're going to ignore it and recognize that 0.167 molarity of that is going to create 0.167 molarity of that. This is hydronium, so if I log it, I'm getting my pH directly. So that works out to, I gotta do that again, log 0.167, 0.777, or pH of that. So, in the first region of this graph, if we imagine, when we start with, this is going to be volume of base, and this is going to be pH. We start with a pH that's very low, below 1, and it's going to cook along here for a little while until we hit the equivalence point. At the equivalence point, we expect it to rise suddenly, but let's just go ahead and find out what pH it'll rise through during that equivalence point. So, just erasing all this stuff and going back to right here, I am going to stop talking about A, because I've done that one now, and I'm going to talk about B. So now we're on this one. I haven't changed the amount of sulfuric acid or the concentration of sulfuric acid, so I'm still dealing with 0.05 moles of that, but now I have 100 milliliters of my sodium hydroxide. So I have a concentration of 0.5 molarity and a volume of 0.1 liters. That's 0.05 moles. And now you can see why we call this the first equivalence point, because the number of moles of sulfuric acid and sodium hydroxide are equal, hence equivalence point. When these things react, that means that they'll react to completion. It is an acid-base reaction, so it happens quantitatively, leaving none of this and none of this. And now all of a sudden these weak species that are created through this initial acid-base reaction become very important. See, if there's nothing of the strong acid and there's nothing of the strong base, then the weak things are going to dictate the pH. So this starts at a value of 0, and when I subtract 0.05 away from those, I create 0.05 moles of this. So I have a final concentration of 0.05 moles of HSO4-. Here, again, I'm going to start working with an equilibrium, so I need the concentration. That's moles over volume. So I have 0.05 moles divided by my new total volume, which is 100 plus 100, or 200 milliliters, or 0.2 liters. This is going to give me a concentration of 0.25 molarity. With that in hand, I can do my second acid-base reaction, HSO4- plus H2O goes to SO4 2- plus H3O plus. This reaction is a weak acid reaction, and so it occurs in equilibrium. I start with an initial concentration of 0.25 molar. I don't care about my population of water because it's liquid, so it doesn't affect the equilibrium. And I'm going to assume I haven't made any of this yet, and I'm ignoring my native population of H3O plus. The equilibrium will shift towards the side that has zeros. And so if I have my initial, my change in my equilibrium will be 0.25 molarity minus x, 0 plus x, and 0 plus x. So there we go. I want to use the 100 rule here, or I always kind of look for that. But if I look up in a book for the Ka2 process for HSO4, I'm going to find out that it has 1 times 10 to the negative 2. So if I take 0.25 divided by 0.01, it's only going to be 25, which doesn't meet our threshold for the 100 rule, so we can't do it. Also note here I'm using the Ka2 because I'm talking about the second hydrogen process for sulfuric acid. It lost its first one, so now it's on its second one. So with that in mind, the Ka is equal to 1 times 10 to the negative 2, which is going to be equal to the concentration of H3O plus times the concentration of sulfate divided by the concentration of bisulfate. And again, we're ignoring water because it has a constant concentration. I prefer to get out of scientific notation, especially when the number is as manageable as that. And so I get this equation. 0.01 equals x squared, 0.25 minus x. So I'm going to get 0.0025 minus 0.1x, or 0.01x equals x squared. And so if I move everybody over to the right hand side, 0 equals x squared plus 0.01x minus 0.0025. Alright, annoying, but I have to use a quadratic formula. Negative b plus or minus the square root of b squared minus 4ac divided by 2a. A is 1, so that's convenient. So I got negative 0.01. I can't have this result as a negative, so I'm only going to worry about the positive root. 0.01 squared minus 4 times my c, which is going to be negative 0.0025, divided by 2, and I'm just going to punch this out. And I get x equals 0.4045. So with that in hand, if I go back up to my original equilibrium and I look at my H3O plus, I can see that x gives me my H3O plus concentration, so this concentration is H3O plus, which is 0.045, which means if I want my pH, I can log it directly. And that's going to be negative 1.347. Remember, it's negative log, so negative negative, or just a pH of 1.347. So this equivalence point that we talked about right here is going to swing up through 1.347. So this is going to be 1.347. It's going to sort of level out at that point and continue to increase as a weak acid titration would in the next region. And to get the pH in that region, I'm going to do one more of these calculations. I think I'll try and do that one, and then having done that one, I'll pause the video, and just to break it up, create a secondary video where I do those last two. So I think I'll make this in 2 videos because it's getting a little bit long. Just erase this all up. Okay, so we finished this one, the first equivalence point, and now we're going to deal with a volume of 150 milliliters of sodium hydroxide. Again, the acid-base reaction, the initial reaction that's going to happen here, is that first proton process from the sulfuric acid producing HSO4 minus plus H2O and a little bit of Na plus. So we're going to deal with that. So what's going to happen here is, here I still have my 0.5 molar times my 0.1 liters. I haven't changed my volume or concentration of sulfuric acid throughout. So I still have 0.05 moles to work with that for this reaction. The NaOH, on the other hand, has a concentration of 0.5 molar and a volume of 0.15 liters. And so now we're up to 0.075. We can see we're past our first equivalence point, that when this reaction happens, there's still going to be sodium hydroxide left over. So this is now my limiting reagent. So minus 0.05 and minus 0.05 until that runs out. See, that's gone now, and we're left with 0.025 of this. That is also going to create 0.05 of this. As this goes down, that goes up. And so we have 0.05 of that. So that's the first acid-base reaction. But now we have HSO4 minus. We still have remaining sodium hydroxide population. And so I have to consider the secondary acid process. SO4 minus plus H2O plus even more sodium, which I'm neglecting because he's soluble and ignorable. So I've created 0.05 moles of this, and 0.025 of that is remaining in this reaction. So now in the secondary process, this is going to be the limiting reagent. So I will react that away until it is all gone. And what I'll see is when I do that reaction, I'll be left with some HSO4 minus. Now don't forget that as I react that 0.025 moles of sodium hydroxide away, I'm actually creating 0.025 moles of sulfite. These are moles, and now I'm going to have an equilibrium form between bisulfate and sulfate, so what I have to do is I have to convert them to concentrations to consider the equilibrium. Concentration equals moles over volume, so 0.025 moles in both cases divided by my new volume, 150 plus 100, is 0.25 liters. So my new concentration for both is 0.1 molar. Finally, we can look at that acid-base equilibrium where HSO4, what's left of it, is reacting with water to produce H3O plus when it donates its proton as an acid, and sulfate 2 minus. So 0.1 molar of this and 0.1 molar of this, and I'm still going to ignore my native population of H3O plus. That approximation is getting less and less true, but it's still good enough for what we're doing. It's going to decrease by x, going to increase by x, going to increase by x. That's my initial, this is my change. So at equilibrium, I have 0.1 minus x of this, and 0.1 plus x of this. Now this is still the acid-base reaction for the Ka2, which still has a value of 0.01. Or, if you prefer, 1 times 10 to the negative 2, but as I said before, I like it in that form if it's this simple. That's going to be equal to H3O plus times SO4 2 minus, my products, divided by the variable concentration of bisulfate and ignoring the non-variable concentration of water. 0.01, and I got x being 0.1 plus x, and 0.1 minus x. And again, I would like to use the 100 rule, but I don't have enough of my initial stuff to justify it. If you're thinking about this, this is sort of a common ion situation, and you could ignore x, especially in the bottom, but I'm just going to work through it and do the full quadratic because it's not that bad. So 0.01 times 0.1 gives me 0.001 minus 0.01x equals 0.1x plus x squared, 0.001. I'm going to move everybody to the left-hand side all in one step here. This is going on for a long time, so let's speed it up a little bit. X squared plus 0.11x minus 0.001. Alright, there's my quadratic. I'll use the quadratic formula. Negative b plus or minus square root b squared minus 4ac divided by 2a. Conveniently, a is still 1. And so when I go negative 0.11 here, I know I'm going to need the plus root because I need my x to be positive. 0.11 squared minus 4 times negative 0.001. And I'm ignoring, and then that's all over 2. So 0.11 squared plus 0.001 times 4, square root answer. So I'm getting negative 0.11 plus 0.1269 all over 2. So my x works out to be 0.00844. You could write that in scientific notation, but again, it's not that bad of a number, and I still prefer not to do that. Now all the way back up here, looking at my original equilibrium, this is an acid equilibrium with water still, so I'm still producing hydroxide, or not hydroxide, hydronium. So this is my concentration of hydronium, which if I'm looking for my pH directly, means I can just log it. So I get 2.07. Which means that in this graph, in this region, I'm all the way up around 2, which is like higher, but still fairly lower, reflective of the fact that the result that regardless of the fact that HSO4 is a weak acid, as far as weak acid goes, it's fairly strong. That Ka value associated with this acid is pretty big. So that's our curve to this point. Computer's running out of batteries and this video is getting long, so I'm going to stop it and then I'll pick it up to do the last two.